Hi, I'm Ali Langeberg, and today I'll be talking about stateful analysis and fuzzing of commercial baseband firmware. So, first things first, what exactly are basebands? They are dedicated processors inside your phone running a real-time operating system. There are a few vendors that develop and maintain their in-house baseband firmware. This firmware is responsible for handling cellular protocols from 2G all the way up to today's 5G. In fact, right now there is a baseband in each of your pockets talking directly with cell towers. But unfortunately, this conversation isn't always secure. Attackers using malicious or fake base stations can exploit vulnerabilities remotely simply by sending malicious over-the-air messages. The baseband firmware is usually developed using memory unsafe languages, mostly C or C++. This means they are vulnerable to bugs like buffer overflows. These attacks might start with just disrupting your connection, causing denial of service, but in worst cases, they can even escalate attacks into your phone's main operating system. Baseband security analysis is challenging. Like I said, basebands implement 2 to 5G cellular protocols, which are really complicated. And to achieve this, they run a real-time operating system with over 150 tasks in 5G. Each task typically maps to a protocol layer and handles different responsibilities, like handling OTA messages or hardware interactions like SIM card access to read information requested by NAS layer. These tasks are deeply stateful and interdependent, which makes analysis even more challenging. Looking at prior work, Firmware and BaseSafe use dynamic analysis to fuzz message handlers, but partial emulation needs manual reverse engineering, and full emulation often fails when the target task isn't properly initialized. There is also Basecamp. A static tool only works on integrity checks. So the key question is, how can we uncover deeper state-dependent vulnerabilities without all that manual setup? To answer that, let's look inside baseband tasks. As I mentioned, these tasks are stateful. If we send an over-the-air message to the NAS task, it gets instantly rejected because it's not in the right state. That state, or in other words, what the task has seen or done, is stored in state variables, which are defined outside the message processing loop and persist across iterations. Here is a simplified example which is reverse engineered from a Samsung Shannon baseband. It starts with some initialization code and then enters a loop to process messages. At line 17 and 18, the input is rejected because mmpros and mmas don't satisfy the check. In this toy example, there are just two state variables, but in real firmware, reaching the line 19 requires setting 10 or more. So we need to find these state variables and the right values for them. Symbolic execution can help, but if we make everything symbolic, we hit pass explosion almost immediately and will miss any chance to dig deep into the code. To solve this, Lotus introduces iterative symbolic analysis to identify both state variables and their preconditions. Next, I'll show you how that works using the xMessageHandler function. Like I said, state variables must be defined outside the message processing loop. So the first step for Lotus is to analyze the initialization code and collect a set of candidate state variables. Let's say in this example, it identifies 3 such variables. Next, Lotus needs to figure out which of these variables lead to immediate rejection of a test input. Iterative symbolic analysis helps to gradually explore the code a bit more every time and avoid pass explosion by building upon previous results. In the first iteration, when execution reaches the xMessageHandler function, it hits line 15. Here, message type is assigned before it's ever read. Because of that, Lotus removes it from the candidate set. Its value cannot persist through iterations, and it's not a state variable. Then Lotus proceeds to the branch condition on line 16, and we follow the path where the input is an over-the-air radio message. The execution continues to line 17, where mm plus is used in a branch condition. As mm plus is read without prior assignment in a branch condition, it is confirmed as a state variable. In this iteration, since mm plus is not symbolic, it retains its initialized value of 0, representing 5G mm plus null, which does not satisfy the branch condition, so execution cannot proceed down this path. In the second iteration, mm plus is now treated as symbolic. This lets the analyzer explore both sides of the branch on line 17. It reaches the path leading to line 18 and records a precondition on mm+. Next, MMAS is used on line 18 in a branch condition and will be added to the set of state variables. Repeating for another iteration enables access to line 19 and records a new precondition. And solving these preconditions will allow the fuzzer to properly initialize the target task. By following this workflow, analyzer ultimately discovers all preconditions required to reach the radio message decode function. Here is a high-level overview of LORIS, which takes a baseband firmware binary as input. At the core is our analyzer, which performs iterative symbolic analysis to automatically uncover state variables and the preconditions needed to reach deep code execution passes. To manage path explosion, analyzer also uses state variable ranking and checkpoint-based path pruning. I won't go into those details today, but they are key to the scaling of the analysis. LORIS also includes two supporting components, the emulator and the fuzzer. However, for today, I'll only really briefly touch on them. And the emulator builds on Firmware, but we extended it to support newer Samsung 5G Exynos basebands. On the fuzzing side, we use a grammar-aware fuzzer. It generates valid NAS messages automatically, so no seeds or manual harnessing required. This design lets LORIS explode complex, stateful code passes that previous tools couldn't reach. Well, can LORIS find real bugs? It uncovered 7 previously unknown exploitable vulnerabilities, including integer, heap, and stack overflows. All were confirmed by Windows and assigned CVEs, with some rated high or critical severity, including one triggered by a malicious SMS. To validate them, we replayed LORIS-generated inputs using a modified open-source core network and sent them over the air to real devices. In every case, the baseband crashed immediately, which was confirmed through logs and the disappearance of signal bars. While some bugs cause denial of service, others can escalate to remote code execution or data leaks when chained with other exploits. And we evaluated LORIS across 5 different commercial devices from 2 major vendors. In the basic block coverage figure here, you can see that LORIS consistently outperforms both Firmware and Grimoire, even though those tools can rely on manual harnessing to reach meaningful coverage. Interestingly, even without grammar support, LORIS still reaches similar coverage, though it takes more time. To conclude, we built LORIS, which is a framework for stateful analysis and fuzz testing of baseband firmware. LORIS employs an iterative symbolic analysis that progressively uncovers state preconditions while effectively mitigating the path explosion problem. Using LORIS, we discovered 7 new remote vulnerabilities and triggered them over the air. LORIS is released right now for the community to use. We encourage you to try it out. I really appreciate your time and thank you all.